Here is a strange thought to fall asleep to. Almost everything you have ever watched leave the ground was never meant to arrive anywhere. A rocket is, by design, a machine built mostly to disappear. 90% of it, sometimes more, is fuel. Matter that exists only to be burned and thrown away within minutes of leaving the pad. The astronauts, the satellite, the tiny sliver of purpose at the tip. That is the smallest part of the whole. Everything else is a controlled explosion, shaped, aimed, and sacrificed just so a small thing can go up, while a much larger thing falls behind it, spent and forgotten. You have spent your whole life underneath that idea without ever quite looking at it directly. So look at it now, gently in the dark. You're lying still. Maybe the room is quiet. Maybe there's a soft hum somewhere, a fan, a radiator, the hush of a city outside the window, the settling of an old house. Somewhere above you, past the ceiling, past the roof, past the sky you can't even see from where you're lying, there are objects moving. Satellites, fragments of old boosters. Perhaps, if it happens to be passing tonight, the International Space Station, drifting silently at about 7.8 kilometers per second, circling the planet roughly every 90 minutes. A bright, steady point of light for anyone patient enough outside to watch it cross the sky in a matter of minutes. None of that would be there if humans hadn't spent centuries chasing a single, almost absurd idea that you could throw something away fast enough and in the right direction to make something else fly. Let your breathing slow. We're going to go back, not to the moon landing, not to the space race, though we'll pass through both eventually. We're going all the way back, past rockets as weapons, past rockets as science, back to a much smaller, much older fire, in a place and time most people never think to associate with spaceflight at all. It begins, as far as historians can trace it, with any real confidence, in China, sometime around the 9th century, with what appears to have been an accident. Alchemists, working in the Tang dynasty, were reportedly experimenting with mixtures of minerals in search of an elixir of immortality, a substance that might extend life indefinitely. The irony of that is worth sitting with for a moment in the dark, because what they found instead was a mixture of saltpeter, sulfur, and charcoal that had a troubling tendency to combust violently. They had not found a way to preserve life. They had found gunpowder. It took a few more centuries for that discovery to become a weapon, refined slowly through trial and accident rather than any single deliberate leap. By the time of the Song dynasty, in the 12th and 13th centuries, military records describe what are usually translated as fire arrows, ordinary arrows fitted with small tubes of gunpowder that would ignite and propel the arrow farther and faster than a bowstring alone ever could. Some historians place a documented use of true rocket-propelled fire arrows around 1160 or so, during conflicts between the Song and the Jin dynasty to the north, though the exact dates, and even the precise mechanism used, are debated, pieced together from fragmentary and sometimes ambiguous historical texts, rather than any single clean origin story. Historians of early Chinese technology often caution against being too certain about which specific battle marks the first rocket, since the line between a fire arrow and a true self-propelled rocket blurred slowly, over generations, rather than arriving all at once. Think for a moment about what that early device actually was. mechanically, stripped down to its simplest form. A tube sealed at one end, packed with a chemical mixture that burns rapidly and produces hot gas far faster than that gas can escape through the tube's open end. The gas has to go somewhere. It rushes out the back under enormous pressure, and by simple physical necessity, a principle nobody in the 13th century had any language for. The tube itself is pushed the other way. Nobody in Song Dynasty China understood this as equal and opposite reaction. They didn't need to. They only needed to notice that when you lit the fuse just so, the thing flew, sometimes wildly, sometimes dangerously, and that this was, on balance, worth pursuing. This is where the story does something rockets themselves do, constantly throughout their history. It branches, scatters outward, and slowly reconverges somewhere else, carried by people who never met each other, and often never even knew of each other's work. Knowledge of gunpowder and gunpowder weapons moved gradually westward along trade routes and through military contact, including during the Mongol campaigns of the 13th century, which connected an enormous span of Eurasia under something close to a single political and commercial network, however violently that network was formed. From there, the idea of the rocket entered the Islamic world and eventually Europe. For hundreds of years afterward, rockets remained mostly what they had always been: unreliable, wildly inaccurate weapons on the rare occasions they were used militarily, and increasingly elaborate fireworks for festivals and celebrations. More spectacle than science. They were beautiful. They were loud. Almost nobody yet understood, in any rigorous sense, why they worked. And so, almost nobody could reliably improve them. That began to change in India in the second half of the 18th century under a ruler named Tipu Sultan, who governed the kingdom of Mysore in southern India and who deployed iron-cased rockets against British East India Company forces during the Anglo-Mysore Wars, particularly in battles fought in the 1780s and 1790s. These Mysorean rockets used iron tubes rather than the more fragile bamboo or paper casings common elsewhere, which allowed for considerably higher internal pressure, more propellant packed into a smaller space, and, as a result, meaningfully greater range. Accounts from British officers present at the time suggest ranges of roughly 1 to 2 kilometers, a genuinely alarming distance for a battlefield weapon of that era. The British were, by most surviving accounts, deeply unsettled by them, both by their range and by the psychological effect of watching flaming projectiles arc unpredictably across a battlefield, sometimes trailing smoke and sparks in ways that spooked cavalry horses and disrupted infantry formations. And in a pattern that would repeat again and again throughout this entire story, defeat became inspiration. An English artillery officer named William Congreve studied captured examples of these Mysorean rockets after Tipu Sultan's eventual defeat and death in 1799, and in the early 1800s developed his own version, refined through his own experimentation at the Royal Arsenal in Woolwich, what became known as the Congreve rocket. The British military used them in the Napoleonic Wars against French positions, and, more famously, to some listeners, during the War of 1812, in the bombardment of Fort McHenry, near Baltimore in September of 1814. If the phrase, "the rocket's red glare," sounds familiar from somewhere, that's not poetic invention or exaggeration. Francis Scott Key, Watching that bombardment from a ship in the harbor was describing actual Congreve rockets lighting up the night sky. As he wrote the poem that would eventually become the lyrics of the American national anthem. And yet, for all their drama and their genuine military utility, these rockets were still fundamentally crude instruments. They tumbled in flight. They wobbled unpredictably, even with stabilizing sticks attached to try to keep them flying straight. Their accuracy was poor enough that they were used more for area bombardment and psychological effect than for precise targeting. Nobody had yet asked the deeper question hiding underneath all of it. Not simply, how do we build a slightly better rocket? But why does a rocket work at all, in a rigorous mathematical sense? And what are the actual physical limits of what one could ever be made to do? That question needed someone who wasn't a soldier or a battlefield engineer chasing an immediate tactical advantage, but someone willing to sit alone for years with nothing but pure mathematics and an unusual kind of patience. That someone was a partially deaf schoolteacher living in a small provincial town called Kaluga, south of Moscow, largely self-taught, largely ignored by the scientific establishment of his era. His name was Konstantin Tsiolkovsky, and he had lost most of his hearing to scarlet fever as a child, which cut him off from ordinary schooling and, by his own account, pushed him toward reading and independent study instead. He spent much of his life isolated by his hearing loss, by his remote geographic location, far from Russia's scientific centers, by the sheer unfamiliarity, even strangeness, of the questions he was asking. While supporting himself as a school teacher, he built a small laboratory at home, conducted his own experiments, and thought obsessively and carefully about the mechanics of flight beyond the atmosphere. In 1903, the very same year the Wright brothers were coaxing a fragile wooden aircraft off a sandy beach in North Carolina, Tsiolkovsky published a paper with a title that translates roughly as Exploration of Cosmic Space by Means of Reaction Devices. In it, he laid out what is now called the Tsiolkovsky rocket equation, a deceptively simple relationship connecting how much a rocket's velocity can ultimately change, how fast its exhaust gas leaves the engine, and the ratio between the rocket's full mass at launch and its empty mass once the fuel is spent. Here's where it gets interesting, and it's worth slowing down for, because this single piece of mathematics quietly governs everything that happens for the rest of this story. The equation reveals something almost cruel. A rocket's final achievable speed depends not simply on how much fuel you cram inside it, but on the ratio of fuel mass to total mass. And that relationship scales logarithmically rather than in a straight line, which means that adding more and more fuel gives smaller and smaller returns the further you push it, because more fuel is itself more mass, which then requires still more fuel just to lift and accelerate that additional fuel. It's a bit like trying to become wealthier by carrying around larger and larger sacks of coins to pay for the privilege of carrying them. At some point, almost all of your effort goes toward moving the payment itself, and only a sliver is left over for anything else. Tsiolkovsky had, from a small wooden house in provincial Russia, with no laboratory budget and no institutional support, uncovered the exact mathematical wall that every rocket engineer since has had to find some way to climb over. He didn't stop there. He proposed liquid propellants instead of solid gunpowder-based fuels. correctly reasoning that liquids would burn more efficiently, more controllably, and could be throttled or shut off, unlike a solid charge that, once lit, simply burns until it's gone. He proposed the idea of multi-stage rockets, the practice of building a rocket out of several smaller rockets stacked together, so that each stage, once its fuels is exhausted, can be discarded entirely, along with its now useless empty tanks and structure, so that the next stage isn't wastefully hauling dead weight any farther than it has to. This single idea, stage separation, turned out to be one of the most important practical solutions to the cruelty of his own equation, because it meant a rocket didn't have to fight its own increasing mass all the way to orbit. It could shed that mass in pieces along the way, becoming lighter and more efficient exactly when it needed to accelerate the hardest. Almost none of what Tsiolkovsky wrote was built during his own lifetime. He died in 1935 in relative obscurity outside the Soviet Union, having done nearly all of the essential theoretical groundwork that everything afterward would rest on, without ever once seeing a rocket built to his own specifications leave the ground. Meanwhile, on the other side of the world, a quiet, awkward, physically frail American physicist was trying to build the very thing Tsiolkovsky had only calculated, without any apparent knowledge, at least initially, of the Russians' published work. His name was Robert Goddard, a professor of physics at Clark University in Worcester, Massachusetts, and he had been fascinated by the idea of rocket flight since childhood, in part due to chronic poor health that kept him out of school for long stretches and left him with plenty of time to read and imagine. By his own account, he traced part of his fascination to reading H.G. Wells's novel, The War of the Worlds, as a teenager, and to a particular afternoon in October of 1899, when he climbed a cherry tree in his family's backyard in Worcester, and, looking out over the landscape, found himself imagining what sort of machine might be capable of reaching Mars. He later described that afternoon as a turning point, and for the rest of his life, he kept a small private tradition of marking the anniversary of that day. Goddard was cautious, private, almost secretive about his research, partly because in 1920 he published a modest technical paper, mostly concerned, in its actual substance, with using rockets to carry scientific instruments high into the upper atmosphere. That included one brief, speculative paragraph suggesting a large enough rocket might someday be capable of carrying a payload as far as the moon. The press seized on that single paragraph and ran with it, largely ignoring the careful technical work that surrounded it. The New York Times responded with an editorial mocking him, arguing that a rocket couldn't possibly function usefully in the vacuum of space because it would supposedly have nothing to push against once it left the atmosphere. A fundamental misunderstanding of Newton's third law of motion, since a rocket, as it happens, pushes against its own expelled exhaust gas, not against the surrounding air at all. If anything, a rocket performs slightly better in a vacuum than in air, since it doesn't have to fight atmospheric drag. The editorial went further, dismissively suggesting that Goddard seemed to lack the knowledge ladled out daily in high schools. It's worth sitting with that for a moment, in the quiet. A working, credentialed physicist publicly ridiculed in the nation's paper of record for holding a position that was, in fact, correct about physics that his critics had simply gotten wrong. Goddard, deeply stung by the mockery, became guarded and reclusive about his subsequent research for the rest of his career, increasingly reluctant to publish details or speak with journalists, preferring to work quietly with a small, loyal team. Funded in later years by the Smithsonian Institution and by the philanthropist Daniel Guggenheim. But on March 16, 1926, on his Aunt Effie's farm in Auburn, Massachusetts, in a snow-covered field, Goddard quietly launched the world's first liquid-fueled rocket. It used gasoline and liquid oxygen as propellants, an approach directly in line with what Tsiolkovsky had theorized decades earlier, though Goddard appears to have arrived at the idea largely independently. The rocket, later nicknamed Nell, rose about 12.5 meters into the air, flew for roughly 2.5 seconds, reached a top A speed of around 100 kilometers per hour, and landed in a cabbage patch approximately 56 meters from where it had launched. By any modern measure, it was a tiny, almost comical achievement, a flight shorter than the time it takes to read this sentence aloud, covering a distance you could walk in under a minute. But it was the first time in human history that a machine built on the liquid fuel principle had actually left the ground under its own power in a controlled, documented flight. Nobody outside a handful of witnesses knew it had happened. There was no press conference, no announcement, no headline. There was only a small, awkward, injured by ridicule man, a modest, snowy field in New England, and a machine that worked, however briefly, exactly as the mathematics said it should. It's a strange kind of justice that, in 1969, as Apollo 11 prepared to leave for the moon, the New York Times published a formal, if somewhat wry, correction to that 1920 editorial, acknowledging that rockets do in fact function in a vacuum, as well as, or better than, in an atmosphere, and stating that the paper regretted the error. Goddard had died in 1945 of throat cancer at the age of 62. He never saw the apology printed. He never saw the moon landing that his own patient, ridiculed cabbage patch experiments had helped make conceptually and technically possible. While Goddard worked in relative isolation in America and Tsiolkovsky worked in isolation in provincial Russia, a third figure was doing something structurally similar in Germany, a Transylvanian-born physicist named Hermann Oberth, who, in 1923, published his own influential and mathematically rigorous work on rocket theory and the possibility of space travel, titled The Rocket into Planetary Space. Oberth's writing, more than either Tsiolkovsky's or Goddard's at the time, captured the public imagination in Germany, partly because it was published at a moment of considerable German cultural fascination with science fiction and technological futurism. Around Oberth's ideas grew something remarkable, an amateur rocketry club called the Verein für Raumschifffahrt, or VFR, translating roughly as the Society for Space Travel, founded in 1927 in Breslau. It attracted hobbyists, engineering students, and dreamers of every kind, people who believed, with a sincerity that would have seemed almost eccentric to most of their contemporaries, that spaceflight was not idle science fiction, but a genuine, solvable engineering problem, one that simply hadn't been solved yet. Among the younger members of that club was a teenager, later a young engineering student, named Wernher von Braun. He was talented, ambitious, aristocratic by birth, and thoroughly captivated by Oberth's writing and by the club's amateur rocket experiments, which included launching small liquid-fueled test rockets on the outskirts of Berlin at a site the club nicknamed the Rocket Airfield. And here the story takes a turn that it would be dishonest and frankly disrespectful to history, to soften or skip past. As the 1930s gave way to the rise of the Nazi regime in Germany, and as private amateur rocketry became increasingly difficult to fund and even legally restricted, von Braun's rocketry work was gradually absorbed into the German military. He became the technical director of a program based at a secluded research facility on the Baltic coast called Peenemünde, developing what would eventually become the A4 rocket, known to the wider world, once deployed by its propaganda designation, the V2, short for Vergeltungswaffe 2, or Vengeance Weapon 2. The V2, first successfully launched on a test flight in October of 1942, was the world's first long-range guided ballistic missile and the first man-made object to reach the edge of space, briefly crossing what is now loosely called the Kármán line, an altitude of roughly 100 kilometers commonly used as a symbolic boundary of space. During some of its higher test trajectories, it was, mechanically and in terms of pure engineering, a genuine leap forward, liquid-fueled, using ethanol and liquid oxygen, capable of supersonic flight, and guided by an onboard gyroscopic system that allowed it to hit distant targets with far more consistency than any rocket weapon before it. It was also, without any softening, a weapon of terror. Beginning in September of 1944, Nazi Germany launched thousands of V-2 rockets against London, Antwerp, and other Allied cities, killing an estimated several thousand civilians in those bombardments. And its production carries a darker weight still, one that historians increasingly insist on, including in any honest account of this period. The V-2s were manufactured largely using forced labor drawn from concentration camp prisoners at an underground manufacturing facility called Mittelwerk, dug into a mountain near the Mittelbau-Dora camp, under conditions that surviving accounts and later historical investigations describe as brutal in the extreme. Malnutrition, disease, physical abuse, and executions of suspected saboteurs among the prisoners. Historians estimate that more people died producing the V-2 than were ever killed by the weapon in combat use against Allied cities, a genuinely staggering inversion of what a weapon is usually understood to cost. Von Braun's precise degree of direct knowledge of and personal involvement in those specific conditions at Mittelwerk remains debated among historians, with some emphasizing his documented visits to the underground facility, and others emphasizing the limits of what can be conclusively proven about his day-to-day awareness. What is well documented, and not seriously disputed, is his proximity to the program as its technical leader, and his willingness to accept formal SS membership and continued state support in order to keep his rocketry research funded and moving forward, even as the human cost around him mounted. It's an uncomfortable thread to carry into a story that later becomes, in America, a story of heroism and wonder. And it should stay uncomfortable, rather than being smoothed over for the sake of a tidier narrative. After Germany's surrender in 1945, in what the American government called Operation Paperclip, the United States quietly brought von Braun and roughly 120 other German rocket scientists and engineers to America. offering them positions developing American missile and, eventually, civilian rocket programs, in effect, absorbing an enormous amount of hard-won technical expertise, while largely setting aside, at least for the time being, any full public reckoning with what had produced it. Von Braun would go on to lead the development of the very rockets that eventually carried American astronauts to the moon. Both of those facts are historically true, sitting uneasily next to each other, and neither one erases or excuses the other. The Soviet Union, arriving in the eastern parts of collapsing Germany around the same time, was doing something structurally similar, capturing V-2 hardware, technical documents, and German engineers who had not already fled or been captured by the Americans, and building its own early rocket program partly around that captured knowledge. But the Soviet effort quickly developed its own singular, central figure, a man named Sergei Korolev, whose story is, in its own very different way, just as haunting as von Braun's, though it runs in almost the opposite moral direction. Korolev had been a promising young Soviet rocket engineer and glider designer in the 1930s, associated with early Soviet rocketry research through a state-sponsored group studying jet and rocket propulsion. In 1938, during the height of Stalin's political purges, he was arrested on fabricated charges of sabotage, subjected to torture during interrogation, reportedly including a beating that permanently damaged his jaw, and sentenced to hard labor. Most accounts place him, for a time, in brutal conditions in the Kolyma region of Siberia, one of the most notoriously lethal parts of the Soviet Gulag camp system, where the combination of extreme cold, malnutrition, and forced labor killed enormous numbers of prisoners. He survived that period, though not without lasting damage to his health, before eventually being transferred to a special prison design bureau, known in Russian slang as a sharashka, where imprisoned scientists and engineers were forced to continue technical and military research under close state supervision in exchange for somewhat improved living conditions. He was eventually released and, remarkably, rehabilitated within the Soviet system, going on to become the secretive, publicly unnamed chief designer behind the Soviet Union's greatest early space achievements. His identity was kept a closely guarded state secret for years, in part out of a genuine fear that Western intelligence agencies might attempt to target or assassinate him if his name and role became publicly known. He carried the physical effects of his imprisonment, including that damaged jaw and chronic health problems, some related to the poor medical care available to him afterward, for the rest of his life, even as he oversaw a program that would repeatedly humiliate the very Western powers whose fear of him had helped keep his identity hidden. Under Korolev's direction, on October 4, 1957, the Soviet Union launched Sputnik 1, a polished aluminum sphere about 58 centimeters in diameter, fitted with 4 long trailing antennas, weighing approximately 83 kilograms. It carried no scientific instruments beyond a simple radio transmitter, emitting a steady, repeating beep on frequencies that amateur radio operators around the world could pick up on ordinary equipment as the satellite passed overhead every 96 minutes or so. It did nothing, in a narrow technical sense, except exist, transmit its beep, and orbit the planet. And yet it proved, undeniably, and to a global audience, that doing so was now possible. Try to imagine for a moment what that must have genuinely felt like in America. In the autumn of 1957, stepping outside on a clear night and knowing with total certainty that a man-made object launched by a geopolitical rival was passing silently somewhere overhead, faster and higher than anything any nation had ever built before, and that you personally had no way of stopping it, or even fully understanding how it had been done. It set off what's now remembered as the Sputnik crisis, a genuine wave of public anxiety and political urgency that reshaped American science funding, science education policy, and military strategic thinking almost overnight, contributing directly to the later creation of NASA and to significant new federal investment in mathematics and science education across American schools. The United States rushed to prepare its own response, and after an embarrassing, widely publicized failure of the Vanguard rocket in December of 1957, a launch broadcast live on television, in which the rocket rose only about a meter off the pad before its engine lost thrust and it collapsed back down in flames. An event gleefully reported by international press under headlines like Flopnik and Kaputnik. America finally succeeded on January 31st, 1958, with the launch of Explorer 1, carried aloft by a Juno rocket developed, in a somewhat pointed historical irony, by Von Braun's own team, now working for the American Army. Explorer 1 carried a small, relatively simple scientific instrument built by an American physicist named James Van Allen, and it made a genuine, lasting scientific discovery, not merely a symbolic political victory. The instrument's data revealed the existence of what we now call the Van Allen radiation belts, vast donut-shaped bands of charged particles trapped by Earth's own magnetic field, encircling the planet at certain altitudes. It's worth pausing on that for a moment. In the dark, the very first American satellite born directly out of panic, humiliation, and international rivalry, humiliation and almost host as an aside, still managed to teach humanity something true and permanent about the invisible structure of the space immediately surrounding our own planet. Later that same year, 1958, the United States government formally created NASA, the National Aeronautics and Space Administration, consolidating several existing research bodies, including the older National Advisory Committee for Aeronautics, into a single civilian agency dedicated to aeronautics and space exploration. The long, quiet chain reaction that Tsiolkovsky's equations and Goddard's Cabbage Patch rocket had set in motion decades earlier, almost unnoticed at the time, was now a matter of national policy, enormous public funding, and open international rivalry. The Soviets kept their early lead for a while longer. On April 12, 1961, a 27-year-old Soviet Air Force pilot named Yuri Gagarin became the first human being to leave Earth's atmosphere and complete a full orbit of the planet aboard a spacecraft called Vostok 1. The flight lasted about 1 hour and 48 minutes from launch to landing. Gagarin reportedly remarked, upon looking out at the planet from orbit, something to the effect that the Earth appeared blue and beautiful, an observation that has been repeated, translated, and slightly mythologized over the decades since, with the exact original wording varying somewhat between different accounts and translations, though the essential sentiment appears consistently across sources. He returned to Earth by ejecting from the descending capsule at high altitude and parachuting down separately as was standard procedure for that early Soviet spacecraft design, landing in an open field near the Volga River, where, according to often repeated local accounts, he reportedly startled a farmer and her young daughter who had never seen anything remotely like a man in a bulky orange pressure suit descending by parachute out of an empty sky. Just over 3 weeks later, on May 5, 1961, American astronaut Alan Shepard flew a much shorter suborbital flight aboard a capsule called Freedom 7, becoming the first American in space, though not yet the first American in full orbit. That particular milestone came the following February, in 1962, with John Glenn's orbital flight aboard Friendship 7. And here is where the story's chain reaction accelerates dramatically, driven as much by politics and public sentiment as by pure engineering ambition. In September of 1962, President John F. Kennedy delivered a speech at Rice University in Houston, framing the space race not merely as a technical contest between rival superpowers, but almost as a moral and civilizational test, famously declaring that the nation chooses to go to the moon not because it is easy, but because it is hard, because that particular challenge would serve to organize and measure the very best of the nation's energies and skills, rather than because it offered any immediate practical benefit. It was, in its way, as much a piece of political theater as a statement of engineering ambition. But it committed genuinely enormous resources toward a single, staggeringly specific, and very publicly stated goal. At its peak, the Apollo program consumed roughly 4% of the entire United States federal budget, a scale of public investment in a single technical project that has rarely been matched before or since. The task of actually building the rocket capable of reaching the moon fell, in large part, to von Braun's team, now based at what would become NASA's Marshall Space Flight Center in Huntsville, Alabama, and their creation was the Saturn V. Still, to this day, among the most powerful rockets ever successfully flown to full operational completion, its exact ranking, depending on how one compares it to certain 21st century designs that have since approached or exceeded six specific performance figures. The Saturn V stood roughly 111 meters tall, taller than most cathedrals ever built, and generated approximately 3.4 million kilograms of thrust at the moment of liftoff, an amount of raw mechanical force that shook the ground and rattled windows for kilometers around the launch site at Cape Canaveral. It burned through the enormous kerosene and liquid oxygen-fueled first stage in under 3 minutes, discarding it, exactly as Tsiolkovsky had theorized more than half a century earlier, the instant its fuel was spent, letting it fall away into the Atlantic Ocean so the rest of the rocket could continue upward, lighter and faster, without the dead weight. On July 20th, 1969, Apollo 11's lunar module, nicknamed the Eagle, touched down gently on a relatively flat plain called the Sea of Tranquility, with astronauts Neil Armstrong and Buzz Aldrin aboard, while a third astronaut, Michael Collins, orbited alone above them in the command module, farther from another human being at that moment than anyone else in history had ever been. Armstrong's words as he stepped down onto the lunar surface a few hours later, "That's one small step for man, one giant leap for mankind," have been repeated so many times in so many contexts that they've almost worn smooth, like a stone handled too often by too many hands. But it's worth remembering. in the particular quiet of tonight, that those words were spoken by a real, nervous, physically exhausted human being, standing somewhere no living thing had ever stood before, roughly 384,000 kilometers from the room you happen to be lying in right now, held there by an unbroken chain of ideas that stretched back through Korolev's frozen labor camp, through von Braun's complicated and morally compromised choices, through Goddard's quiet cabbage patch experiment, through Tsiolkovsky's isolated, deaf, uncelebrated calculations, all the way back to a Chinese alchemist more than 1,000 years earlier, searching for immortality and finding gunpowder instead. After Apollo, the chain didn't stop, though its pace and its shape changed considerably. Public and political enthusiasm for extremely expensive lunar missions faded fairly quickly once the initial competitive goal had been achieved, and NASA shifted its focus toward the Space Shuttle program, which began carrying astronauts into orbit in 1981 with the orbiter Columbia. The shuttle represented a genuine attempt to make spaceflight somewhat more routine and more economical, largely by embracing reusability in a way the fully expendable Saturn V never had. The shuttle's two solid rocket boosters were recovered from the ocean by parachute after each launch and refurbished for reuse, and the orbiter itself, unlike earlier capsules, was designed to fly again and again, landing on a runway like an aircraft, rather than splashing down once and being discarded. It was, in its own imperfect way, a partial answer to Tsiolkovsky's old, cruel mathematics about wasted, discarded mass. But the shuttle program also carried immense risk, tragically realized on two separate occasions. In January of 1986, the shuttle Challenger broke apart 73 seconds after launch due to the catastrophic failure of a rubber O-ring seal in one of its solid rocket boosters, a seal that had become dangerously brittle in the unusually cold weather at the launch site that morning. In February of 2003, the shuttle Columbia broke apart during its return through the atmosphere due to structural damage sustained on one of its wings from a piece of foam insulation that had struck it during launch more than 2 weeks earlier. Both disasters killed their full crews of 7 astronauts each, and both fundamentally and permanently reshaped how NASA thought about acceptable risk, internal communication, and the specific dangers of allowing something as inherently violent as spaceflight to start to feel routine. In the 21st century, the long chain reaction gained an entirely new kind of participant. Private companies operating alongside rather than only underneath national governments. A company called SpaceX, founded in 2002 by the entrepreneur Elon Musk, with the explicitly stated long-term goal of making human life multiplanetary, spent years absorbing repeated early failures while developing its own family of rockets known as Falcon. And in December of 2015, SpaceX achieved something that Tsiolkovsky himself, working alone with pen and paper in provincial Russia more than a century earlier, might have found almost unbelievable, successfully landing the first stage of a Falcon 9 rocket upright, back on solid ground. Only minutes after that same stage had already delivered its payload most of the way toward orbit. It was, in effect, a fresh and far more ambitious attempt to answer that same century-old problem of wasted, discarded mass, not by somehow making the rocket lighter to begin with, but by making its single most expensive component genuinely reusable. flying itself gently back down under its own remaining fuel and guidance rather than simply falling, spent, into the ocean or burning apart entirely as it fell back through the atmosphere. That single technical achievement, a spent rocket stage flying itself back down, its engines reigniting briefly to slow its own fall, small grid fins and landing legs unfolding, touching down within a few meters of its intended target on a floating platform or a fixed landing pad, has, in the years since, become almost routine, repeated many hundreds of times, and has dramatically lowered the practical cost of reaching orbit. It's a strange, almost poetic kind of symmetry, if you're inclined to hear it that way, lying here in the dark. Modern engineers, standing on top of everything, Congreve and Tsiolkovsky and Goddard and Korolev and von Braun had each contributed in their own very different ways, eventually found a way to make the discarded, sacrificed part of the rocket come home again, intact, instead of being lost forever the moment its job was done. Today, rockets built on these same fundamental principles carry communication satellites that let you make a phone call from a remote mountain road with no cellular towers anywhere nearby. Weather satellites that quietly track the formation of a storm somewhere over an ocean you will probably never personally see, and GPS satellites that continuously calculate your position on the surface of the Earth to within a few meters all day and all night, without you ever having to think about it. The International Space Station has been continuously occupied by rotating international crews since November of the year 2000, the product of a genuinely cooperative effort among multiple nations that were, within living memory, locked in the very geopolitical rivalry that built the rockets to get there in the first place. Robotic missions built on the same basic underlying principles: thrust, mass ratio, staged separation, all still ultimately governed by Tsiolkovsky's original equation, have carried spacecraft past every planet in the solar system and beyond it entirely. Voyager 1, launched in 1977 to study the outer planets, has since left the heliosphere, the vast bubble of charged particles blown outward by our sun, and now drifts alone in true interstellar space, still faintly transmitting data back across billions of kilometers. Still, in the most literal sense, governed by the same simple equation a deaf schoolteacher worked out with nothing more than pen and paper in a small wooden house at the very start of the 20th century. All of that, the steady beep of a polished sphere passing silently overhead in the autumn of 1957, a single boot print pressed into gray. Ancient lunar dust in the summer of 1969, a scorched rocket booster easing itself gently back down onto a landing pad. Decades later, almost as if learning for the first time how to trust gravity again instead of simply fighting it. All of it traces back to the same simple, strange fact you started with tonight, lying here in the quiet, that you can throw something away fast enough in exactly the right direction and call the result flight. You don't have to hold on to any of that now. It can rest at the very edge of your mind the way the night sky rests over a room whose curtains are drawn. Entirely present, entirely real, and yet completely unseen from where you happen to be lying. The equations, the launch dates, the names of men who suffered in labor camps and men who made compromised, difficult choices under terrible regimes, none of it needs to stay awake alongside you tonight. Let the weight of the blanket settle a little more heavily, a little more kindly into your shoulders. Let your hands go loose and heavy, wherever they happen to be resting right now. There is nothing left here to calculate, nothing left to launch, nothing anywhere that needs your attention in order to keep quietly moving. Whatever is above the ceiling, above the roof, above the clouds you cannot see tonight, will keep circling patiently on its own, exactly as it has for decades now, without ever needing you to watch it. Your breath can slow. Just this room, just this quiet, just the dark, holding you gently the way it holds everything else that has for tonight finally come to rest.